Okay, something I'm sure that the test will encounter is route surveying type issues. Horizontal curves and vertical curves are the two big issues that they will be probably testing on. So we're going to take a look at horizontal curves first, and then we'll do verticals secondarily. Okay, so basically your horizontal curves exist in a highway or alignment or maybe other types of things where you've got curvature going on, but you basically have tangent straight lines which are defined. Distance is one component in either a bearing or an azimuth, and then you have horizontal curves. Now, horizontal curves can refer to one of several types. Just the basic circular curve. You could have a compound curve, or you could have a reverse curve, which are basically a combination of circular curves, and then you can have the true spiral curve. So spirals are a little bit more involved. We did not put anything on here on spirals right now, but that could also be something we could look at if people have particular questions on it. So these are examples of the more common horizontal curves. So remember, all of those curves are horizontal. The compound and the spiral and that. But what we have here in the very top, this is your simple circular curve where you have tangent in, tangent out, and tangent curve between, based on the geometry of a circle. The compound curve is composed of two or more curves that are put together. They have one point of tangency between them in this case, but the thing that's different about them is they have different radii. So radius here is bigger than the one coming in. So now you could actually have another one and another one, so sometimes we use compound curves to emulate spirals. A true reverse curve is where you have a circular curve going one direction and it instantaneously changes another. So you typically don't see these like on center lines of highways or anything, but you'll see those a lot of times on right-of-ways. So we're going to take a look at the simple circular curve. So any circular curve is composed of elements. So there's 5 defining elements, or I'm sorry, 8. 3 are typically used in, like, say, descriptions. But you can get by with 2 actually to do any calculation. But we have the central angle, the radius, r. Central angle usually defined by delta. Radius r, t for tangent, long chord is LC, arc length is L. Then we have a degree of curve, DC, and less used quantities are middle ordinate and external. So prominent points or significant stations within a circular curve would be the 3 major ones: the PI, point of intersection; PC, point of curvature; PT, point of tangency; and then any point on that curve is referred to as a POC. So that can just be any random point, but your PI, PC, and PT have prominent positions within that curve. So we have this diagram that is showing you most of those features located on it. So if we go look at this, this is our tangent in. We have a back tangent. This is the lower stations, increasing stations, coming into a point where the tangents are deviating. This is called your PI point. You have to be given as a station. Point of deviation here is what's referred to as delta. Some agencies use I, so you'll see both. It also tends to be this angle down here, which is the central angle of the curve. Now, that's only true if it's 90 degrees here from the tangent to the radius and 90 degrees here, which in a highway it's always going to be. Not always so on boundaries, so you have to be careful with that. PC, point of curvature, that's where this curve is starting. It's a tangency point. PT, where it's ending, it's also a tangency point. So your PT is always going to have a higher station value than your PC. Length of arc is the bend distance around this thing. Going that way, that would be that magenta kind of color line. And that's measured in, I would say, the bend distance. The distance straight shot from PC to PT is your long chord. That's what your EDM would give you if you set up shot. And that's also a working quantity. Then we have the radius. Of course, the radius is the distance from the origin to the PC, origin to the PT, or origin to any point along the curve. If you take a line and drop it from the PI to the origin, that bisects the curve. And if you measure the distance along that bisector from the PI to the midpoint of the arc, you get the external. And from the midpoint of the arc to the midpoint of the chord, you get the middle ordinate. These two are used a lot less often in curve design and or curve layout. So degree of curve, that's kind of a weird one. That's the one, it comes in one of 2 varieties. You either have arc definition or chord definition. Highways favor arc definition, which says this is the angle that subtends 100-foot length of arc up here. So if I measure the bent distance, it's going to be 100, but it's going to be less on the chord. It's kind of a same, it's a way of expressing the radius only in terms of an angle, in my opinion. Then you have the chord definition, which is used primarily on railroads, or I'd say almost exclusively on railroads, where they have, it is the angle that subtends a 100-foot length of chord. So the distance across here, straight shot, is 100 feet, and the bent distance is going to be slightly bigger. Okay, so you need to make sure that you're using the definition of degree of curve if you're using any kind of curve problem. All right, so here's your equations for your typical curves. Tangent, radius times the tangent of half of delta. Long chord is 2r times the sine of half of delta. The arc length can be given by several equations. Delta pi r over 180, or 100 delta divided by degree of curve. So if you're doing highway work, or most work that we would be involved in, these two equations are exactly equal. If you're doing railroad work, this equation will not work for a railroad. You have to use this for stationing purposes. And when we get into L, how that relates, PT minus, actually I've got that reversed, PT minus PC, just the difference is going to be L. So we have degree of curve for the arc definition, and we're not going to do the derivation, but this constant 57.29578 divided by R is going to give you the arc definition degree of curve. And of course, if you know your degree of curve and you want to solve your R, then R is going to be equal to 57.29578 divided by degree of curve. So these guys are just really interchangeable. Middle ordinate, external secant, you can see the equations and relationships here. Again, these are less useful and probably won't be, you probably won't see them as much, but the other ones that we talked about there are very much important. Okay, so we're going to take a look at this little example where we're given a curve that has a delta of 1642 and a pi value of 256340 and a radius, and we want to solve for some of these things. So we're going to solve for the T, the long chord, the L, degree of curve, PC and PT stations. Okay, so this problem we're looking at, we have a given delta of 1642, a pi station, and a radius. So I always like to draw a little sketch. It just kind of helps relate what's going on. So I'm calling this my pi. It really doesn't matter what I'm calling my PC for this picture, but I'm going to call my PC to the left, PT to the right. So we're looking for all those different variables. Typically, it doesn't necessarily matter which order I calculate them in, but I have to have all the other stuff before I get PC and PT. So I'm going to just kind of work down the line here. So T is your radius times the tangent of half of delta, in this case. Okay. Calculating that number, you should get 146.78 feet. Okay. Be careful when you do this, because some people will take the tangent of that number and divide the tangent value by 2, and that's not the same thing. They're close, but they're not the same thing. So there's our T value. To get our long chord is the relationship 2r times the sine of half of delta. So that would be 2 times 1,000 times the sine, 16 degrees, 42 minutes over 2. And if we crank those numbers through, we're going to get 290.44. And of course, should go without saying, if you're in meters, you're getting meter references, distances. If you're in feet, you're getting feet values. So length of arc, delta pi r over 180. So that's one reference. That's one way of doing it, and you get 291.47 if you go through the numbers. Now, once we get degree of curve, we can do that with degree of curve. I'll show you that in a minute. So we have everything we need right now. We have T, long chord, length of arc, we can now get PC. PC is referenced by your PI minus your T. So we're taking 25, 60, 340. We are subtracting the T 146 off of that. So we get 24 plus 16, 62. Okay, so that would be our PC reference. So now, the PT is going to be your PC plus your length of arc. Now what some people want to do is they reference, oh, well this is your T value here. So if I back off by my PC, I can just add to my PCPI to get my PT, and that's going to be totally incorrect. So that's never true. Okay? So it's always going to be PC plus L. So in this case, we're taking 24, 16, 62, and we are adding to it the 291.47. Plus 0.8, 0.9. So that gets us that. So the only other thing we need to now calculate is degree of curve. Degree of curve for a highway, which we're going to assume. You can't assume that though. I'm sure that would be totally spec'd out to you if you were doing this on a test. But we're going to use the 5729. 578 relationship divided by the radius. Basically, you can see our decimal place is moving over. We're going to come up with 5 degrees, 43 minutes, and 46 seconds. If you do that for use any other calculations in that, you've got to recognize that that degree of curve has got a little bit of rounding in it. Okay? Because usually, I'm going to round that to the nearest second. So it's not quite as pure as other numbers. Okay? So pretty straightforward as long as you know two variables. Now, on a test, ideally, they're not going to necessarily give you always delta and R. Okay? So they may have you back into this. So what they might give you, for instance, on a test, you might be given degree of curve, and you might be given delta. Well, that's actually a good thing because degree of curve and radius are just intimately related. So if you know your degree of curve, you know your radius, and you're good to go. Because most of these equations have a radius value on them. Okay, so the other thing you might encounter is horizontal curve layout. There's 3 typical methods. I could see them hitting you with one of these. So deflection angle long chord method, deflection angle and short chord method. So they're essentially very similar in terms of what you calculate. And then if you're doing it radial stakeout, you could calculate coordinates on a curve. That would be a little bit more involved. I don't know that I would see that, but I could say that wouldn't be out of the realm of possibility. So this is showing you the concept of the long chord method. So what we're using is what we call deflection angles and long chords. This is assuming we're occupying a PC point, backsighting our PI. We're calculating an angle, going a distance, another angle, which is called your deflection angle, distance. So these red lines are indicating long chords. This is the long chord, or the longest chord that you'll encounter, so the distance from the PC to PT. So all of these guys are going to be some subinterval of that. These angles are geometrically related to what's happening down here at the center line. So whatever, if I would draw a line from here to that point, that angle is always going to be double what this angle is. So we're going to see how to calculate that here in a second. But this is deflection angle long chord method. This is deflection angle short chord method. So this is basically a bearing distance intersection. So what you're doing, your instrument's occupying the PC. Again, they're backsighting the PI. They're turning the deflection angle, you're going a distance. And then they're going to turn the next angle, and you're going to measure the distance from the preceding. So this is called your short chord. So we're laying out short chord, short chord, short chord. In a typical problem, you're going to have the interior short chords are all going to have the same number, but the starting short chord and the ending short chord are going to be something less than that. So if we're doing a 50-foot layout right here, these are going to be close to 50 feet, but depending on what your stations are here and here, they're going to be something even less than that. And again, deflection angles for this are going to be the same as the deflection angles for the other process, but the only thing we have to reckon or calculate would be these short chords at that point. So, key equations, just really two. And then you have to use the chord equation a little differently for your short chords. So to calculate a deflection angle to any point on a curve, which I'm referencing as d over 2, it's the local length of arc times the degree of curve divided by 200. And the degree of curve divided by 200 is a constant for the curve that you're working on. So once you calculate it, you can just calculate it once and store it. So we have then L is just the distance in stations from where you're sitting to where you're going. So you're always going to stay put at the one point, PC or PT. So my distances are just increasing as I go around. Long chords to any station are just going to be 2 times the radius times the sine of the deflection angle. Do not divide this angle by 2. It's already divided by 2. So you just, whatever you calculate, you just plug that in direct. For the short, go ahead, that's good. For the short chord, this is basically the same equation, but the difference is that we're calculating what's called a deflection increment. So that's just the difference between 2 deflection angles. So if I'm going from station 20 plus 50 to 20 plus 75, the difference in those 2 deflection angles will be my deflection increment, and that's how I calculate the short chord between those 2 guys. So this is showing you again the calculations, how this works. So this is your deflection angle, d over 2 angle. This is your chord. This is your length of arc to that station. So you calculate the length of arc to the station you want to go to. Plug it into that L times degree of curve divided by 200 equation. It's going to yield this for you. And then plug that number into this equation, and that's going to give you that. So it's pretty simple. Okay, so a simple deflection angle problem. You're going to occupy a point. In this case, we're going to assume we're occupying the PC. We also are going to lay this curve out at some interval, so like 50 feet, 100 feet, whatever, or every 25, every 50, every 100. So we're going to do this every 100 feet. So every 100 feet means we're going to go to the next full station. So we would not be at 25 plus 1662. We would be at 25 plus 00. We're going to go to 25 plus 00. And then 26 plus 00, and then ultimately 27 plus 00, and we're going to deflect into the PT, which is going to be at 27 plus 0809. So if you were breaking that up into a tighter interval, you'd be 25 plus 50, 26, 26 plus 50, so it just depends. You can also start here and work backwards, so you can go either way. So the first calculation is nothing because we're already sitting there, so there's no L, there's no degree curve, there's no any of that. So the first thing we're going to do is calculate the L distances. So simply all we're going to do is subtract those 2. That's going to get us the distance between. So we subtract that, we get 83.38 feet. So then this L is just another 100 feet, so that becomes 183.38. Subtract again, we get 283.38. Ultimately, subtracting PC and PT, we should come up with what our initial L value was in this, which happens to be 291.47. So this is the big part of your setup right here. The rest of it is just following things formulamatically. So what we're going to do to calculate each deflection angle, we're just using the L times degree of curve divided by 200. So what you should reference here or recognize is that degree of curve divided by 200 is a constant. So therefore you can take that number and store it, and then it's just recall times L, recall times L, recall times L to graph these numbers. So in my case, we have L, our degree of curve is 5 degrees, 43, 46, dividing that by 200. So you can take that number and literally just store it. Okay? Now, the one thing I like to do first is the last deflection, because this guy should always be half of this. And if it's not, we've got a problem. So your last deflection should always be half of delta. So if we plug in 291.47 times that relationship divided by 200, calculating this, what I get is 8 degrees, 21 minutes, and 0 seconds, which clearly is half of delta. Now, sometimes it won't be exact, and partially that's going to be because this guy's a rounded number, remember, so it's not going to be perfect, okay? It's just going to be partially right. So if that's good, then you can just go through and then just plug that in, and plug that in. So after I do that, I'll notice these are incrementing. And I got 2 degrees, 23.19, I got 5 degrees, 15, 12, and I have 8 degrees, 0.7, 0.6, and ultimately the last one. The other thing you'll notice is that these guys have the same deflection increment. They're based on 100 feet. So the difference between this and this and this and this should be the same. And basically it's going to be half a degree of curve. So you can kind of use that as a check. So once we have that done, we can start plugging and chugging long chords. Long chords are based on the relationship 2r sine your deflection angle. So we basically have 2 times 1,000, so this is 2,000, that's going to be a constant, and then you're just going to plug in this number, take the sine, times 2,000, that number, take the sine, just to keep doing that. So if we do that, we notice we get, for the first one, I get 83.35, and you should notice that this is going to be slightly less than this, because of course, this is the bent distance, and this is the straight shot. As we go through, we're going to see that deviation a lot more. 183.12 versus 183.38. Further out on the curve. And then ultimately, there's our last, whoops. Yeah, that's it. That's our last one. Okay? So, just strictly using this equation, but everything's based on this, okay? So you blow this, you got a problem, which is ultimately this, okay? So just check things. Here's the key thing. This should be delta over 2 within some couple of seconds, okay? If it's not, you got a problem, okay? Then there's no point in calculating anything any further. So short chords. So here's kind of the rule. The short chords, the first short chord, or the first long chord is always equal to the first short chord, so you just pop that guy over here. So these short chords then, we're going to do a short chord from 25 to 26, so you're taking an increment of 100 feet, and then this will be 100 feet. So these two short chords will be the same. The last short chord here is going from 27 to 27.0809. So there's an 8-foot distance here, so you're going to have 1, 2, 3 short chords. Now, you've got 2 ways to do it. You can subtract this angle from that angle and plug that into that equation to get your short chord, or you can take 100 feet and you can plug it into this equation to get your increment to do it. So either way works, okay? So if I took 100 feet, plugged it in there, I would get a number that I could multiply, or again, I could just subtract those 2. What you should come up with is a number that's going to be close to 100 feet in this case. I came up with 99.96. And it should be the same for this one to this one. Okay, that's the same one, same value. So the last value is based on the increment between 27 and 27.0809. So again, if you subtract those 2 and plug that into here, or you pop 8 feet, 0.09 into here, you're going to get the same angle either way, and then you're going to get a very small chord, and it's approximately going to be the same number, which it is here. Okay? And there's your short chords. Alright, so taking, if we wanted that station, we just subtract from the BBC to where we want to go. That gives it in feet, convert it to stations, plug the stations in, and when you run the equation through, this is what you're gonna come up with for that. So that gives you the elevation of the point on the parabola at that point. So you can literally just go any point you want on that parabola.